right, hello. So today we're going to be discussing the reaction quotient and how we can use it in conjunction with LeChatelier's principle. It's a French guy, LeChatelier. Okay, so first off, we need to figure out what LeChatelier's principle is and what it has to do with the system at equilibrium. So first, instead of talking about LeChatelier's principle, we're going to talk about something new that we can calculate. So we can calculate something called a reaction quotient, okay? The reaction quotient is represented with the letter Q, capital Q. Okay, now the thing about the reaction quotient is that it's calculated exactly the same way we calculate K, the equilibrium constant. However, when we are solving for Q, the concentrations and pressures that we're using, the numbers that we're plugging into it, represent a system that is not at equilibrium. So remember that K, our equilibrium constant, is calculated using equilibrium concentrations and pressures. Okay, so when we calculate K, we know that our system's at equilibrium, and we know that those concentrations are equilibrium concentrations. If we're not sure that the concentrations we have or the system we have is at equilibrium, then we're probably calculating Q. So we're using values for concentration or pressure of a system that is not yet at equilibrium. Now we can compare our reaction quotient to our equilibrium constant K in order to determine whether before this thing gets to equilibrium, more reactant or product is going to form. Okay, so right now my numbers are not at equilibrium. Eventually it's going to get to equilibrium. Before it does that, are we going to have to make more reactant or make more product? If we end up making more reactant, we call that a shift. And since the reactants are on the left side of an equation, if we have to make more reactant before it reaches equilibrium, we call that a shift to the left. Okay, because reactants are on the left. If we are going to end up making more product before we reach equilibrium, then it's going to be a shift to the right, because products are on the right side of the equation. Okay, how do we calculate the reaction quotient? Like I said, the formula for calculating the reaction quotient is exactly like the formula for calculating your equilibrium expression. It's going to be your reactants, your products over your reactants, everything held to the power of its coefficient. The only difference is that the values you're plugging in for each of these things do not necessarily represent a system at equilibrium. So if I had this weird skeleton equation here with the capital and lowercase letters, the lowercase letters represent the coefficients. It would be the products, so capital C to the power of little c, capital D to the power of little d, over my reactants. So capital A, little a, capital B, little b. Okay, so products over reactants. Well, once I calculate Q, which is easy enough, right? How am I going to know whether it's going to shift left or shift right? So you're going to have to calculate Q using the concentrations and pressures that are given to you. Now, if they tell you that those values are equilibrium values, then you're calculating K. If they've not told you that you're at equilibrium, you're calculating Q. All we have to do is compare the two values. We have to compare K to the reaction quotient, Q. And here's the easiest way to do it. Like, this is the easiest way to figure out shift left, shift right. Always put the letters in alphabetical order. So K first, and then Q. You get a value for both, right? You get a value for K, and then you calculate a value for Q. Let's say that K is greater than Q. As long as you have K on the left and Q on the right, if K is greater than Q, you can turn that into an arrow, and that arrow is pointing to the right. It's going to shift right. Okay, if K is greater than Q, what that means is I need more product, because when K is a larger number, that means that the products are greater than the reactants, right? And so in order to get more products, in order to increase Q, to make it the same as K, to make it equilibrium values, we've got to make more product. If K is equal to Q, that's when we're at equilibrium. So if you calculate Q and you determine that it's the same value as K, then you are actually at equilibrium. So no shift is going to occur. You're already at equilibrium. If we calculate and we see that Q is greater than K or K is less than Q, again, you turn that into an arrow. As long as you do K and then Q, you can take this sign, turn it into an arrow, and it's going to shift left. Okay, so what that means is my Q value is too big. It is too great a number. We need to increase the bottom of our proportion, aka the reactants, right? Because the reactants are underneath the products in our equilibrium expressions. We need to increase the concentrations of our reactants in order to bring that proportion down. And in order to do that, we're going to have to create more reactants. So it's going to shift to the left. Okay? So that's Q. But what does that have to do with LeChatelier's principle? Okay, so the thing is, let's say you're at equilibrium already. There's no more shift occurring, but then you do something to it. If you apply stress or change to a system at equilibrium, it's going to cause a shift to occur. So it's going to make it go left or right. It's going to create either more reactant or product until equilibrium is restored. So what are stresses? Changing concentrations would be a stress. So if all of a sudden I add more reactant or add more product, that would change, my system would have to adjust in order to reestablish equilibrium. Changing pressure would be a stress, and changing temperature would be a stress. Okay, so all of those three things could affect my system and cause a shift to occur in order to reestablish equilibrium. So let's say that we add more reactant. My system's at equilibrium, and then all of a sudden I dump more reactant in there. Well, if I've got too much reactant, in order to readjust my numbers so that I get my equilibrium constant back to what it was, if I add more reactant in order to reestablish equilibrium, we're going to have to make more product. And if we're making more product before equilibrium is established, then we are shifting to the right. Okay, now on the other hand, if I add more product, now I have too much product in there. Well, then I have to get rid of product and I have to make more reactant in order to reestablish equilibrium. Okay, and since reactants are on the left, we would say it would need to shift left. Okay. Again, instead of adding to our concentrations, we could take away from our concentrations. So let's say we remove reactant. If I remove reactant and I have a void there for the reactants, I'm going to need to make more reactant. I'm going to need to use some of my product, make more reactant in order to bring my proportion of product to reactant back to my equilibrium value. And so if we're going to make more reactant, then that is a shift to the left. Okay, same thing. If I remove product and I'm missing product, I'm going to have to make more product in order to increase the amount of product and decrease the amount of reactant until I get back to my equilibrium values. And so if we're making more product, that's a shift to the right. Okay, let's say that instead of changing concentrations or amounts of reactant and product, and by the way, before I actually move on to this next part, if what you're removing or what you're adding is not actually in the equilibrium expression, it's not going to cause a change. So remember that solids and pure liquids are not included in equilibrium expressions. So if you add more solid, that literally does nothing mathematically to your reaction quotient. It does not change anything. It's not going to affect equilibrium. So sometimes you'll see questions where they add, you have an equation and it's a mix of solids and gases, or aqueous solutions and solids and gases. If they change the amount of solid, if they remove solid on the reactant or product side, or if they add solid, since it's not in the equilibrium expression, it mathematically makes no difference, and there's going to be no shift, so no change would occur. Okay, that's a really important point to make. An increasing pressure really only affects systems where there are gases. Okay, so if there are no gases present in the equation, if there are no gases in the equilibrium expression, then it's not going to change anything. But if you have a system with gas and you increase the pressure, it's going to shift to the side that has fewer moles of gas in order to relieve that excess pressure. Okay, so it's going to shift to whatever side of the equation has the fewest moles of gas. Similarly, if we decrease the pressure, then we are going to need to increase the pressure somehow, and the way that it's going to do that is it's going to shift to the side of the equation that has more moles of gas. So another thing, there are thermochemical equations where heat is included in the equation. So you'll see a value in kilojoules. If you see the heat as a reactant, it is endothermic. That means that energy is entering the system as a reactant. You will see heat given as a product in exothermic equations, where heat is giving off by the reaction. So think of adding heat or taking away heat, aka cooling something down, as adding or taking away reactant or product. So let's say that the value for energy is on the product side. It's an exothermic equation. Well, if I heat it up, then I am increasing product, and an increase in product is going to cause a shift back to the reactant side. So that would be a shift to the left. That's how that one would work. And so we'll see more examples of these throughout the homework, but I just wanted you guys to be familiar with the different kinds of stresses that could cause a shift in equilibrium, or to reestablish equilibrium once equilibrium is disturbed. So make sure you guys understand how these changes could cause a shift left or shift right. Also make sure that you guys know how to set up your expression for your reaction quotient, that you know how to calculate the reaction quotient, and that you know how to compare it to your equilibrium constant in order to determine whether a system is going to shift left or shift right before you reestablish equilibrium.